All right, welcome. Today we're jumping right into a core concept from Precalculus, one that, believe it or not, shapes our entire universe in more ways than you'd think. We're talking about the ellipse. So what do these things have in common? Well, the answer is this really elegant mathematical shape. It's not just some squashed circle, you know? It's literally the blueprint for everything from the paths of planets to these incredible architectural marvels. And today, we're going to decode it together. So here's our game plan. We'll start with why ellipses are so important in the first place. Then we'll get into the nitty-gritty of the equation, work through a few problems, I'll show you the common mistakes to watch out for, and we'll wrap up with a really cool, kind of mind-bending real-world application. First up, let's talk about why you should even care about this shape. I promise, it's not just for a math test. It's actually fundamental to understanding the world and the universe all around us. That's right. Every single planet in our solar system, Earth included, travels in an elliptical orbit around the sun. So if you've ever thought about being a rocket scientist or an astronomer, well, mastering the ellipse is your first giant leap. Now, let's get to the heart of it all, the math. But don't worry, think of this equation as the DNA of an ellipse. Once you get it, you can basically build or analyze any ellipse that comes your way. Okay, this is where we start. This is the standard equation for an ellipse that's sitting perfectly centered at the origin, at 0, 0. It looks pretty simple, but all the power, everything that matters, is in those two little letters on the bottom, A and B. They control the whole thing. So, here's the most crucial point. A and B give us the major and minor axes. That's just a fancy way of saying the long and short diameters of the ellipse. And here's the golden rule. You absolutely have to burn this into your brain. A squared is always the bigger number in the denominator. That one little fact tells you if the ellipse is wide or if it's tall. All right, two more key terms. The vertices? They're just the endpoints of that longer, major axis. Easy enough. But the foci? Oh, the foci are the secret sauce. They're these two special points inside the ellipse that give it all its unique properties. And remember this, they always, always, always lie on the major axis. So how in the world do we find these mysterious foci? Well, we use this simple, really elegant formula. C is just the distance from the center out to each focus. And look closely, see that minus sign? That's key. You just take A squared minus B squared to get C squared. This little formula is what unlocks the location of those all-important foci. Okay, enough theory. The best way to really understand this stuff is to see it in action. So let's put these formulas to the test with a couple of classic examples. Okay, check out this equation. First step, find A squared and B squared. What's the rule? A squared is the bigger one, right? So that's got to be 25. That means A is 5. B squared is 9. Next, we just plug them into our key formula. C squared equals 25 minus 9. That's 16. So C is 4. And since the bigger number was under the x squared, we know the ellipse is horizontal. So the foci are at -4 and +4 on the x-axis. See? Simple as that. Now let's try working backwards. This time, we're given the vertices and the foci. Okay, so the vertices are at ±8 on the y-axis. That tells us two things right away. A equals 8, and our ellipse is vertical. It's a tall one. The foci are at ±5, so C equals 5. We use our key formula again, C squared equals A squared minus B squared, but this time we're solving for B squared. So 25 equals 64 minus B squared. Do a little bit of algebra, and boom, B squared is 39. Now we just build the equation. Since it's vertical, the bigger number, A squared, which is 64, has to go into the y squared term. It just perfectly shows how all these pieces fit together. All right, we've seen how to get it right, but let's take a minute to talk about how it can all go wrong. Seriously, this section right here could save you a ton of points on your next homework or test. Oh man, I've seen it time and time again. There are basically 3 classic traps, and they are super easy to fall into if you're not really paying attention. So let's just break them down so you can completely avoid them. Okay, first up, mixing up A squared and B squared. Just tattoo this on your brain. A stands for awesome because it's always the bigger one. Second, putting the foci on the wrong axis. Just remember, the foci live on the major axis. No exceptions, ever. And finally, using the wrong formula for C. Which brings us to maybe the most common mix-up of all. It's so easy to get these confused. For our ellipse, it's subtraction, A squared minus B squared. But for a hyperbola, which we'll probably learn about soon, it's addition. It's such a tiny difference on the page, but it has huge consequences. For ellipses, just think you subtract to keep the foci inside the shape. All right, for our last section, let's talk about the most magical property of an ellipse. This is where all that math, all those letters and numbers, becomes this really fascinating real-world experience. This is the big secret of the foci. If you build a room with an elliptical ceiling and you stand at one focus, any sound you make, even a tiny whisper, bounces off the walls and converges perfectly at the other focus. It's like having a secret acoustic targeting system built right into the room's geometry. It's amazing. And this isn't just some theoretical party trick. It's a real feature in some of the most famous buildings in the world. From National Statuary Hall in the US Capitol Building to St. Paul's Cathedral in London, you can actually go and experience this incredible property of the ellipse for yourself. It's math that you can actually hear. So there you have it. From planetary orbits to architectural wonders, the ellipse is absolutely everywhere. The blueprint is simple, and now that you know how to read that blueprint, I'll leave you with a question. Where are you going to spot one next?